So here on one board, we have all of 802. So I'm going to start today with a lightning review of the entire foundations of 802, all of which we've built up over the course of the semester so far. So here's my E&M review. First item is Maxwell's equations, which I've written out over here. So here are Maxwell's four equations. Let's remind ourselves what they say in qualitative terms. How do you, when you see equations like this, what do they tell you before you do any math? So Gauss's law, this first equation here, tells us that electric charges, rho, density of charge, makes electric fields. Then this second one, magnetic Gauss's law, if you misinterpret it, it sort of says there's nothing in the universe that makes magnetic fields. And that's not exactly right. What it says is, as we've discussed at length, is that there are no magnetic monopoles in the universe. And if there were magnetic monopoles, they would make magnetic fields, but there aren't any magnetic monopoles. That's what this one says. Then we get to Faraday's law. Faraday's law says, hey, there's another way to make electric fields, and that is if you have a time-varying magnetic field, that's going to make electric fields. And then the last one, the Ampere-Maxwell equation, tells us that actually there are two ways of making magnetic fields, even though this sounds like no monopoles, no field, but there are in fact two ways of making magnetic fields. The first term here, which is the term that Ampere discovered, says that electric currents, moving charge, electric currents make magnetic fields. And then the last term here, which we introduced most recently, and this is the piece that is due to Maxwell, says that if I have a time-varying electric field, an electric field that's changing in time, that also makes magnetic fields. So I can get magnetic fields either from electric currents or from time-varying electric fields. This is the foundations of 802, together with these other ancillary facts, all of which you've seen. So here I have three ancillary facts. First of all, charge is conserved. What that says is if I have any volume, if the charge in the volume is increasing with time, there must be electric currents coming in from outside through the edge of the volume, bringing the charge in. That's the conservation of charge. Then the Lorentz force law, and this is in fact where we started, because the first term here, this is Coulomb's law, which is where we started 802. The Lorentz force law says, what do these electric and magnetic fields, whose dynamics is now the main object of our interest, but what do they do to charges? Well, they exert forces on those charges. An electric field pushes charges around, and a magnetic field pushes charges around if the charges are moving, because the magnetic force is proportional to V cross B. So if the charges are at rest, the magnetic field is not going to push them. So this is the Lorentz force law. And then the last thing here is just a reminder that these electric and magnetic fields, whose dynamics we're now studying, carry energy. There's an energy density associated with E squared or B squared. So if I have electric or magnetic fields in some volume of space, there's energy there, which can be used to do work. And this too we've seen earlier in 802. So this is all of 802. And now what we're going to do is we're going to see how waves come out of this. And I want to really stress that this is one of the greatest examples in science of you get more out than you put in. These equations were derived by Coulomb and Ampere and Faraday and Maxwell to describe electric charges and electric currents, and together with the Lorentz force law, how the charges and currents make fields, and then the fields push charges around. That's what these were developed to describe. These came out of a long series, 100-year series of experiments and careful observations of phenomena involving charges and currents. So now what we're going to do is we're going to get rid of the charges and currents. We're going to ask, what do Maxwell's equations describe in vacuum? So I look for the charges and currents on the board, and I cross them out. So no charges anymore, and no currents anymore. So I just crossed out the charges and currents. That means I just crossed out the whole starting point of electricity and magnetism, the people who first discovered these equations were using them entirely to describe the physics of charges and currents. And now I'm saying, well, let's look at these equations in a case where there are no charges and no currents. So this is Maxwell's equations in vacuum. What kind of solutions do these equations have if there are no charges and no currents? Well, there's one obvious solution, and that's E equals B equals 0. Let's just check and make sure. If E is 0, well, this equation is satisfied. If B is 0, this is satisfied. If E and B are both 0, this is satisfied. If B and E are both 0, this is satisfied. So if there are no charges and currents, one perfectly legitimate solution to Maxwell's equations is no fields. No E, no B, nothing. But the amazing thing, which we're now going to discover, is that these equations, when I've crossed these two terms out, have other solutions. They have solutions that describe waves, electromagnetic waves, that describe light. And this was not at all anticipated by the people who were first figuring these equations out, because they were trying to describe other phenomena, seemingly unrelated phenomena involving charges and currents. And now what we're going to see, as Maxwell himself was the first to discover, that in the absence of currents or charges, there are still very interesting and non-trivial solutions to these equations describing what we now call electromagnetic waves. So this is where we're going.